Welcome to Ask and Learn.
So continuing on with our work around physical chemistry, taking a look at gases, moles, pressures, vapor pressures and things as alike, we can first start off with some contextual learning. So the extraction is a process of separating substances from a mixture based on their solubilities or their relative solubilities. So the solute is extracted from the carrier using the help of some sort of solvent, and the extraction is the minimum of the three components processes. So the extraction is a tertiary system. So from 50% relative saturation relation, we have gamma naught P is equal to 0.500 pH star. Gamma naught is the mole fraction, P is the pressure, pH star is the vapor pressure. We substitute in the vapor pressure as 1068 millimeters of mercury. P is 760 millimeters of mercury. Gamma naught becomes 0.703. So the saturation relation at the outlet stream, we have pH star is equal to 0.05 P. Get that in millimeters of mercury, so then we multiply 0.05 by 760 millimeters of mercury, so we get pH star is equal to 38 millimeters of mercury. And so from the answer and equations, the temperature at saturation can be calculated as negative 3.26 degrees Celsius. Mole balance of the condenser is as follows. We have N naught is equal to N1, add 1.5 kilomole, add 1 take away 0.703 multiplied by N dot naught is equal to 0.95 N1 dot. So we have equation 2 and equation 3. So then we generate N dot naught is 2.81 kilomoles per minute, and N dot 1 is equal to 0.682 kilomoles per minute. And so the moles of nitrogen in the outlet stream is 0.6479 kilomoles. Volume of nitrogen, we have 14.5 SCMM. So the flow rate of nitrogen to the dry is 14.5 SCMM. Moving on to part B now, so we have the relation for the 50% relative saturation at the condenser inlet is as follows. So we have 0.50 pH star is equal to gamma naught P. We rearrange and substitute P in, so we get pH star, vapor pressure is equal to 10,685.6 millimeters of mercury. So from equation 1 that we saw previously, the temperature at saturation, T0 is 187 degrees Celsius. So the saturation at the outlet condenser, pH star is 0.05 P, and now we can multiply 0.05 by 7600 millimeters of mercury, so pH star becomes 380 millimeters of mercury. So moving on, so from previous equation we have the outlet temperature at saturation T1 that we can define as 48.2 degrees Celsius. So the ratio of the volumetric flow rate of leaving and entering the condenser, we have V dot 1 divided by V dot naught is equal to N1 RT1 over P divided by N2 RT2 over P. So we substitute in our moles of our N1 and our N0 that we defined previously, our T1 and our T0, which is 321 Kelvin and 460 Kelvin respectively. So we have V1 over V0 is 0.682 kilomoles per minute. multiplied by 321 Kelvin divided by 2.18 kilomole per minute multiplied by 460 Kelvin. We get a value of 0.22, so therefore the final gas temperature is 48.2 degrees Celsius, and the volumetric flow rate is 0.22. So for part B, cost of compressing and cooling at 10 atmosphere is required, and for the first part, the cost of cooling to negative 3.24 degrees Celsius, as well as the installation cost and the cost of utilities that we'll need, are required to find the cost effectiveness of part A and part B that we looked at. And so therefore we can determine that part A is more cost effective.